So the next part that we take up is essentially trying to reduce the order of the system if that is possible. When could that happen? Suppose by chance you know a function which satisfies the equation. Okay, forget about the initial data. You know that if you have a basis for the solution space of the homogeneous system, then every solution comes up as a linear combination of these basis solutions, and therefore the coefficients in the linear combination can be computed by setting up the initial or making the linear combination to satisfy the initial condition. So that's the standard process. So we find out what is called x1, x2, xn, a basis for this. That is a solution space. And then any general solution is of the form xt equal to c1 x1 plus cn xnt. Find c1, c2. Now these xi t naught are vectors in Rn. Now you see that x1 t naught is linearly independent. Okay, x t naught is given. Okay, suppose it is something like y1, y2, etc., yn. Then you can write down the components. So what you get is n linear equations to determine c1, c2. And is it possible to solve them? It's quite simple. I mean, not simple, but it is quite feasible, because you see that the coefficient matrix is these are the column vectors that you have. Okay, so this is the coefficient matrix that you have. And you know that these vectors, these columns are all linearly independent. Therefore, the determinant of this matrix is not equal to 0. Okay, therefore, you can solve these n linearly independent, n equations, linear equations, to determine c1, c2, etc., cn, to get the unique solutions. So that is no problem. Okay. So let us leave it at that. Now the question is this: suppose you know one particular solution. You know that it's not an easy task to get a basis of a solution, basis for the solution space. And suppose you know that one particular solution, then we show that this may be used to reduce the problem to solving an n-1 order system. This is a nth order system. Okay, and here you reduce it to an n-1 order system. So it's actually n first order equations that make an nth order system. So what you do is if you know one solution, then you can reduce the problem to solving an n-first order system. That means you will have to work with only n-1 solution. So in short, if you are working with a second order system, something like dx1 by dt equal to dx1 by dt x2. To find a basis for this, for the solution space of this homogeneous system, you get two functions, namely x1t, x2. Suppose by some method you know one of the solutions, not necessarily this, some solution of this or some function, some vector valued function which satisfies this equation, then you can use that to reduce the order of the system. That means essentially it will lead to solving a single equation, single first order equation, which can be sometimes solved by integration, or even that may be difficult. It's a linear equation, so it may not be difficult to solve it. Okay, so you get the second solution. Suppose you take a 3 by 3, a third order system, then what happens is, suppose you know one solution, then you can reduce it to solving a second order system. And if further you know another solution of the second order system, then you can reduce it to solving a first order system, and then or a first order equation, and then because it's a linear equation that you end up with, you can solve it without much difficulty. Okay, so that's the procedure. Okay, so we show this. So we prove the following theorem. Suppose a solution has been found is known for on some interval t1 less than t less than t2, then I can make use of this solution to reduce the order of the equation. say xt where xt equal to, it has n components, eta 1 t, eta 2 t, these are the components of the equation. Now assume one of its components we shall say without loss of generality, because this is developing a technique. Assume eta n this is again, you cannot expect the eta n to be completely not equal to 0 on the interval t1 to t2 if that is the interval on which the equation is defined. But at least see, there will be a small interval which again we designate as t1 to t2 on which eta nt is not equal to 0. So we are assuming eta nt is not equal to 0. Then the equation 1, so I call this one, may be reduced to a system of order that means n minus 1 first order equations, simultaneous equations. So let us, it's a simple procedure, I mean it's not much. So we define new dependent variables y1, yn. Using x1, x2, etc. xn and x. X is the particular solution that we have assumed. This is done as follows. Yit is defined as xit minus eta it divided by eta n t. We are assuming eta n t is not equal to, vanishes nowhere on that. This you define for I equal to 1 to n minus 1, and ynt defined as the differential. So this, let me denote this by 2. Then you see, you can get back xi's from this. Once you know y's, xi's can be obtained from this, because all that you need is that let us obtain this. Okay, let us write down the whole thing. This is possible. Defined. It's well defined. It may not be the same interval that I started with. So you can write if you want it. Then one can immediately write down what are these xi's. This is just a computation. See, to get clarity, what you do is you take a second order system in the sense that a pair of first order equations, simultaneous equations in with independent variable t, and then work with that. Okay, then you will be clear. So after that you generalize. Generalization is no problem. Also, you can get back xit in terms of yn. N minus 1 and xn equal to this is the working backwards, so call this thing. Now you see that if you know xn, then you know yn. If you know yn, then you know xn. These two systems, then you can write down the equation corresponding to yn. So for that we will compute the derivative. Just verify this. dy by dyi by dt equal to dxi by dt minus xn dt of so it is immaterial what these eta n's are and what their derivatives are. In a specific problem we can actually work them out. So this is for n equal to 1, I equal. So this you can mark as now substitute in 1. That's the original system that we started with. For dxi by dt, and then rearranging one gets another set of equations. We obtain, it's a very simple work. One to n. So this is a new system of equations that you get. So the first system, the system that we started with, can be reformulated into bij's, I mean this equation, and the bij's are continuous functions. That's simple to see. This is immaterial what these functions are, because 1 by eta n does not vanish anywhere, so you see that they are a smooth function, differentiability, etc., etc. So there is no problem. Now what we observe is that the two systems are equivalent, by which we mean, suppose you solve the system 5, then you know the solution of system 1 and vice versa. Okay, so the two are equivalent systems. Now let us make an observation on what these solutions are. Suppose you now look at see, we started with these solutions. What is the corresponding solution for 5? Let's see. So look at this relation between xi's and yi's. Okay. Suppose xi equal to eta I and xn equal to eta n, then what you get? Yi is equal to 0. So that is yi t 0 for I equal to 1 to minus 1, and this is equal to 1 I equal to. That is easy to check. Okay. So if xi equal to eta I and xn equal to eta n, then you see that yi is 0 and yn equal to 1. This is for I running from 1 to n minus 1. This is something that you can easily check, verify. So we have translated the problem to a new problem, and we have also identified the solution corresponding to the solution that we started with. We are going to make use of this. Okay. So you can actually see the reduction coming here. Now you see that yi equal to 0. Oh.